Here I am Vadel Sagar, and welcome to the part number 20 of the present discussion regarding the first chapter of electric charge and field. Without wasting time, let's go for the example number 1.15, because in the part number 19 we've seen up to 14th example. So let's go for the 15th one. The question is, consider a uniform electric field E is 3 into 10 to the power 3 in I cap. It means in x direction it is given. What we have to find? A, what is the flux of the field through the square 10 centimeter on a side whose it's parallel to the y and z axis. Once you have one square which is parallel to the yz axis. If it is on the, now you have to imagine where is the yz axis, and it is a parallel to it, so it means a perpendicular to the x axis, and your electric field which is present in a x axis, and your flux, it means your square plate which is present perpendicular to the x axis. Okay, then our electric field can pass through it. Is it valid condition? You can do the further calculations. B task we will see in a later. Whatever the first task, let us find. Okay, A, the electric field which is A is 3 into 10 to the power 3. It is yellowish highlighted one. We are not bothering to the direction, so we are taking the mode of its 3 into 10 to the power 3. Side of the square is 10 centimeter. Then the square we have, so the 10 and 10 multiply, it's the area of the square is the 10 multiplied by 10 is the 100 centimeter square. It's gonna be into the meter square. In the SI systems it will be 0.01. From the at the end you have to take the 0.01 for the further calculation. Now what we have to find, what is the flux? So the flux we have to find, the flux is equal to very fundamental equations, E time of A of actually E dot A. So dot product remove, you have to got the cos theta, E A cos theta, where cos in a present for the present scenario there is a no angle. It means there is a no angle data given, so you have to take for the angle is equal to 0 for your calculation. E is equal to 3 into 10 to the power 3, it is given in a question, and A we find out 0.1 as we seen. Cos is 0, cos 0 1, and further do the calculation in your calculator, you will get the 30 Newton meter square per coulomb. Unit point of view, you have to aware about the what is the unit of electric field, what is the unit of the area unit point of view, it is a meter square, and the Newton per coulomb is the unit of the electric field. So combination of electric field and area, the resultant unit of flux, electric flux, is the Newton meter square upon coulomb. And that is you are my student, so that unit point of view you are clear, and I also very much strict regarding the points or unit. Okay, let's go for them. It is not a new example I am taking again, because of the B task is yet left to discuss. What is flux through the same square? What is flux through the same square what we have in a, which is parallel to the yz and perpendicular to the x? If normal to the plane, it makes 60 angle. Now in earlier case, in earlier example, earlier problem, which is perpendicular, now it is tilted, it is a tilt by 60 degree. Then your at the end we are taking a cos 0. Now onwards for the calculation you have to take cos 60. So let's go for the calculation. 3 into 10 to the power 3, 0.01, cos 60. What is cos 60? Cos 60 is 1 by 2, and then for the calculation is your 15 Newton meter square coulomb. Okay, easy. Let's go for the 1.16 without wasting time. Okay, what is the question? What is the net flux? Again we have to find flux of the uniform electric field which is present in exercise 1.15. Maybe electric field is given 3 into 10 to the power 3 in I cap through the cube which side is 20 oriented so that the face are parallel to the considered plane. Oh, in which square we have to find flux which is parallel to the electric field? Then I can answer it in a without a few second, without in a second, without no, with the, in a second. So this is just all the faces are the parallel to it, therefore the number of field lines which is passes through the cube which is equal to the out, so the resultant flux through the cube which is going to be 0. And that number of time we seen also, we have one cylinder, those two sides are entering and leaving the flux is the same. And there we are seeing from the square point of view, cube point of view, the cube scenario. In this present example, we have a cube. The cube has two parallel sides, six sides are then the three set of parallel sides we have. If they are one of the two sides having the inner and outer flux is equal in amount, so the resultant flux will be the zero. So that is the answer. If it is parallel, then answer is always going to be zero. It should be at angled some angle, or it should be at 90 at the highest point of view. Okay, let's go for the 1.17. Careful measurement of electric field at the surface of black box indicate that the net outward flux through the surface of box is okay. Net outward flux is given as unit through unit. You can judge it is a flux given 18 10 to the power 3. What is the A task? What is net charge inside? Okay, charge we have to find. B task we will see in later. Okay, Q flux is given and the charge we have to find. There is a relationship between phi and Q is only the Gauss law. Phi is equal to Q by epsilon 0, and epsilon 0 we know. The Q we have to find, then epsilon 0 goes up with the phi, then the Q is equal to epsilon 0 times phi. Epsilon 0 is 8.854 into 10 to the power minus 12. Phi is given 8 into 10 to the power 3. You can go and do the calculation. You will reach to 0.07 microfarad. Okay, just the shifting of points, and then this is a common basics understanding of the number systems. Okay, so now what is the B task in the same problem? If the net outward flux through the surface of the box was 0, so we have one box and the net outward flux, it means there is no outward flux, as we seen in the maybe earlier example, that in the cube we have the net effecting force or net effecting flux is going to be 0. Then it is a given now in this our task. If the net outward flux through the surface is becomes were to be 0, could you conclude that there was no charge inside the box? Why or why not? So no, it is not mean that is a always charge. When you are getting the overall flux or the resultant flux outside is 0, it is not a mean that the charge is not inside that Gaussian surface, whether it is box, whether it is cylinder, whether it is anything. It is not a mean that there is a no charge. It means, so what conclusion we made or earlier, what statement we made, it is a wrong. No, net flux peering out through the body depends on the net charge considered in the body. If equal number of positive charge and negative charges, then the resultant charge is not there, but the charges are there. The resultant charge is not there. They are cancelling the effect of the charge. Okay, so that's why it is not a mean that the charges are not there. Charge is not there. Charges and charge. Okay, understand. Let's go for the 1.18. You can take a breath by pausing the video, and I have to go as what I have speed. A point charge 10 microcoulomb is distance 5 centimeter directly above to the center of the square. So what the definition I have, one square you have which is a 10 sides, 10 centimeter sides, and which is of at the above side 10 microcoulombs. So microcoulombs I have to write left. 10 is nothing but the one green one is nothing but the one charge whose charge is 10 microcoulomb, which is a 5 centimeter above than the what you have, paper or plane or whatever it is, as shown in figure. What is the magnitude of electric flux which is passed through that square due to presence of that charge? Hint is very important because that one word is hide there. Think of square as one of the face of cube. This square is nothing but the one of the face of cube. So the one cube is there and a center ma that charge is lised. Okay, now this way you have to imagine. Let's go for the calculation. The square can be considered as one of the face of the cube, which is 10 centimeter side of the center of the charge. As I said you, according to the Gauss law, the total flux through the square is nothing but the Q upon epsilon 0 that we are calculated in this earlier in a chapter. Phi total in a square or cube, q upon epsilon 0. Okay, now there is in a cube we have 6 sides. The total flux can be divided by the 6 time. You can able to say that this much flux is passes through the one of the side of the cube. Okay, so this is the hence the electric flux which is passes through one face of the cube is total phi divided by 6. So this much is your flux, and that flux is the here. Okay, now this flux is equal to that simple flux is equal to q upon epsilon 0, where okay, what we have to find, what is the magnitude of electric flux which is passes through the one of this phi. Okay, the phi is equal to this, phi is equal to this one, which is 6 times less than the total one. What is total? So don't see here, it is a there is a chaos is there. Write in your notebook phi. This phi is your flux which is passes through this one, which is passes through one of the phase. Then it is a phi total divided by 6. What is phi total? Q upon epsilon 0. Put the q upon epsilon 0 upon 6 upon 6. Then your q is given, epsilon 0 you know, which is divided by the 6. You will get your answer. Okay, there is a it is exactly same what I said, but still you can go in the very easier manner. You will get this answer 1.88 10 to the power 5 Newton meter square Coulomb inverse. Okay, let's go for the next example. 1.19. A point charge which is 2 microfarad is the center of the cubic Gaussian surface, 9 coulomb on the edge. What is the net electric flux through the surface? Okay, so one Gaussian surface cube we have, cubic Gaussian surface. So cube we have whose sides are 9 centimeters. At the center we have 2 microfarad, and what is the net electric flux? Again we have to find electric flux. Let's go in a easiest manner, which is a Gauss law. The q phi is equal to epsilon q upon epsilon 0. Epsilon q is given 2 microfarad, 2 microfarad, epsilon 0 is this one. You will directly answer, you will get the answer. It's the easiest example ever I see. 2.26 10 to the power 5 Newton meter square Coulomb inverse 5 unit. Okay, let's go for the 1.20. A point charge causes an electric field. Okay, minus, okay, that electric field is negative electric field to passes through the spherical Gaussian surface whose 10 centimeters. So there now onwards the Gaussian surface is spherical whose radius is 10 centimeter centered on the charge. So if the radius of Gaussian surface were doubled, if the radius of Gaussian surface is double, then what is the flux will what kind of change you can able to see in the flux? That answer you have to made. Okay, a task. Electric flux is given minus 1.10 to the power 3. The radius of Gaussian surface R is 10 centimeter. Electric flux is the pioneer out through the surface depends on the net charge enclosed inside the body. It is not depends on the size of the body. If you have a huge size, it is not means that the huge flux will be passes through it. No, what charges which is inside, its amount of charge will affect on the how much flux will be passes through it. Okay, so the if you are increase your 10 centimeter to the double, it means 20 centimeter. It is not mean that the flux will be enclosing flux will be the increase. No, because if you are increase your area, then you are selecting your slide which is up to pass through it, it will be reduced, but the overall it will be same. Okay, and that may you cleared this idea you may clear in the flux discussion 1.8 number topic, or the 8 one, maybe part number 8. It is regarding the electric flux. If the radius of Gaussian surface is double, then the flux through surface maintain the same flux, which is maintained same, which is nothing but the 10 to the power minus 3 minus 10 to the power 3. What is B task? What is the value of the point charge? Okay, that this much flux can be generated, and what is the charge of it? So again the phi is equal to epsilon 0, then is a q. We have to find what is the value of charge. So the charge q is equal to phi times epsilon 0. Phi is equal to minus 1 into 10 to the power 3 multiply by 8.854 into 10 to the power minus 12. Then you will reduce this to the minus 8.854 nanocoulomb, because 10 to the power minus 9. This much charge, and the charge is negative. It means the flux is negative. It shows that the negative charge inside in the surface of the Gaussian surface. Okay, let's go for the 1.21. Conducting a sphere of the radius 10 centimeter has a unknown charge conducting one sphere. Now imagine one sphere whose radius is 10 centimeter has an unknown charge. You don't know how much charge inside it. If the electric field is 20 centimeter from the center of the sphere, so electric field we have to find at the 20 centimeter. Now you are imagining Gaussian surface is 10 centimeter and you want to find something electric field which is 20 centimeter, which is a farther than the center of the sphere. The 1.5, okay, electric field which is given 1.5 10 to the power 3 Newton per coulomb, and the point radially inward. What is the net charge in the sphere? Okay, this much electric field can be generated. Then what sort of source of it will be? It means charge. Let's go. It's the easiest one. E, the electric field can be generated by the charge. The E is equal to epsilon 0 or the KQ upon R square. It is in a new form, in the new way. E is equal to Q time upon 4 pi epsilon 0 upon D square. D in the sense of R, nothing but the. So you have to calculate, go with the distance between your source to finding point. Here I have to give that diagram so it will be clear to you. But okay, let's imagine this sort of calculation we did in our example also during the chapter. Think about it. One sphere, at the center we have one charge and the radius of this sphere is 10 centimeter, but you have to find your electric field presence at the 20 centimeter. So your distance between your center to that point which is far than the 20 centimeter, you can able to see that there. So your now R will not interfering. D, distance between your observation or distance between your source, which is 20 centimeter. For your calculation in SI, you have to take 0.2 meter. Okay, let's go for the further calculation without wasting time of the epsilon 0 and what it is. We know directly that 9 into 10 to the power 9 is the answer of K directly. So here we have to find Q. Then the rest of the denominator you have bring on the other side. The Q is equal to E time of 4 pi epsilon 0 D square. E you know, 4 pi epsilon 0 you know. Yeah, individual also you can put 4, you can put 5 is 3.14, you can put epsilon 0 8.854 into 10 to the minus 12 you can also put, and D is equal to 0.2 square also you can put, and that answer and this answer will be exactly same, which is 6.67 into nanocoulomb. It means 10 to the power 9 reduces to the n. Small n is the symbol of nano. It is 10 to the power 1. 10 to the power minus 9 should be minus 9. So it is an error here. Okay, I can judge. Let's go for the 1.22. It means 22. Uniform charge conducting a sphere of 2.4 meter diameter has a surface charge density 80 microcoulomb per meter square. So one conducting sphere you have whose diameter is 2.4 meter. It means its radius is 1.2 meter. For your general information, surface charge density, that when you have one sphere, on it charges are there and the density of it means surface charge density sigma is 80 microcoulomb per meter square. What we have to find? Find the charge on sphere. Once the first task is Q we have to find, and the very easy formula we have sigma is equal to Q by A, and that Q we have to find sigma time A. Let's go for the A calculation. A diameter is D, then the R is 1.2. It's very easy, as I said you. Sigma is 80 is given. There's a microcoulomb, so it is 10 to the power 6 for our calculation. We can't go with the 80. SI system must we have to convert. Okay, so then as I said you, this is the fundamental equation is the sigma is equal to Q by A. but it is a Q is equal to sigma time A. This is what Q is equal to charge density, which is sigma time A. Okay, that is your Q as I write here, and sigma is still there, and the surface area of sphere, then the surface area of the sphere is nothing but the 4 pi r square. It is here, and sigma time 4 pi r square. Sigma you know, 4 you know, pi you know, r you know. Put the respective values and you will get your answer 1.447 into 10 to the power minus 3. So I cannot waste in time with the calculation point scenario. You have calculator, do it. I have just guide you what sort of equations, what sort of formula you have to use for the particular problems. I am not wasting time in the calculations. I am giving the answers. You have to check with the calculators and go for the B task. B is your what is total here. What is total electric flux leaving? So here again we have to find flux. Quickly, one word as I said, flux, charge, density, any word I am throwing to you, you have quickly your mind will responding to your formula point of view. Flux phi is equal to q by epsilon 0, density sigma is equal to q upon a. Likewise the formula comes in your brain, then and then you are very succeed in the problems and examples and competitive exams also. Okay, let's go for the phi. This is phi is equal to q upon epsilon 0. As I said you, epsilon 0's chaos is still there. Q you know, not know, you calculate in the above examples. In a task, q is equal to 1.44 10 to the power minus 3. It means millicoulomb. You can use your q here. Epsilon 0 you know, very fundamental constant, 8.854 into 10 to the power minus 12. Then your phi total is equal to 1.63 into 10 to the power 8, as a fundamental unit of the flux is equal to Newton meter square upon coulomb inverse. Upon coulomb bolo, that if you are directly you want to see, then 10 to the power minus Newton coulomb inverse meter square also you can used. Very easy. Okay, you can take a breath by pausing the video, but I can't. I have to proceed for the next example. 1.23, one more examples is left, then after you can take a breath. An infinite line charge produce a field. So the think about it, one wire you have infinite long, then it is generating a field 9 into 10 to the power 9 at a distance of 2 centimeter. So find line charge density. Line charge density, it means the file is open, is lambda. Lambda is equal to q upon L. So that E is equal to q upon q. Okay, what we have to find first of all, an infinite line charge produce electric field. Electric field is given a distance from the what is line charge density, lambda we have to find. Okay, so as I earlier what I said, lambda is equal to charge upon length. It means 2 centimeter, but the charge is not given. That is problem. So that charge we have to link up with the electric field, because electric field is given. So that's why we are putting the E is equal to q upon 4 pi epsilon 0 d. But without all the again task we have to do, already electric field can be generated by the infinitesimal lengthy wire. That's why in our chapters we seen one infinitesimal lines, the last part of the applications of the Gauss law of the infinitesimal lengthy wire, we have electric field generated by the E is equal to lambda upon 2 pi epsilon 0 d. This is direct formula here I am used, because their explanations I did, you may aware about it, and that lambda we have to find, which is nothing but the 2 pi epsilon d time of E. Okay, it is not a de, it is just by the way of writing. D is 2 centimeter, which is a 0.02 meter now onwards. Then your lambda is equal to, don't wasting with the time of this scenario, directly 2 value, pi is 3.15, epsilon 0 8.854 into 10 to the power minus 12, and d is 0.02, E is equal to 9 into 10 to the power 4. You will get this answer. Okay, don't go with the 9 into 10 to the power 9, please, because you have calculator. This is the way it is helpful in a competitive exam where you don't have calculator. There is 9 into 10 to the power 9 is helping a lot. if you can convert 1 upon 4 pi epsilon 0, you can replace 1 upon 4 pi epsilon 0 to the 9 into 10 to the power 9. This will be help you in a competitive exams. But here you have calculator, put the respective values in the same equation here only. Why you are going somewhere else? 2 pi epsilon 0 d and e, all you know, put there, you will get the linear charge density. Last and final, the large thin metal plates two large thin metal plates enclose close to each other. Their inner faces, the plates have surface charge density. So those metal plates having charge, and there is a surface charge density is 17 into 10 to the power minus 12. What is E? So electric field, we have to find what is A task in outer region of the first plate. What electric field in outer region of the A first plate, we have to find electric field in our inner region between two plates. We have to find the electric field in a third plates, it means outer region to the B plates. So the one region number 1, region number 2 inside, and region number 3 outside to the B also. Everywhere you have to find E due to charges which are present on surfaces whose density is 17 times 10 to the power minus 12, sorry 22. Okay, A and B, two parallel plates are there. It's labeled as A and B, and the region labeled as 1, 2 and 3. 1 is labeled as the outer side of the A, and 2 is labeled as the inner region of the A and B, and 3 is the labeled as the outer side of the B. Charge density on the plate A, sigma is this much. Charge density is on B, sigma is 17 minus, it is not mentioned in there, but sigma density, charge density sigma is the mention as 17 times 10 to the power minus 22. Okay, now in a region 1 and 3, electric field will be 0. So task A and B is quickly 0. How? Because charges are not there. Electric field can be there when it enclosed area. Here the electric field is not there because charge is inside. So outside electric field never be possible. So the inner region 1 and 3, electric field is 0. This is because the charge is not enclosed by that respective plates. The electric field can be in the second region because it is inside some system of charge. Okay, so that their electric field E is equal to sigma upon epsilon 0, and that sigma is given, sigma is 17 times 10 to the power minus 22, epsilon 0 you know, so then it is easy for you. One in the important thing in this example is this: the charges is not there outside, it is not enclosing, then it will be the electric will be the 0 on the region of 1 and 3. Okay, so only the region 2 only can be possible which in enclosing the charge, so electric field can be there. Okay, so is there any kind of query or any problem you may face during all the sessions of the 20th or 21st part? You can ask through the contact number, you can ask through the comment section, anywhere, anytime. Thank you very much. We will go for the next chapter soon.